What if I told you that every time you use facial recognition to unlock your phone, or when Netflix recommends you your next binge watch show, you're witnessing the power of linear algebra in action? Today, we're going to learn about neural networks by revealing their mathematical heart. It all comes down to vectors, matrices, and transformations. At their core, neural networks are remarkably elegant. They essentially are composed of linear transformations and linear mappings. Think of them as mathematical machines that takes in an input, transforms it through multiple stages, and produces an output. And linear algebra, that's the language that describes every step of this journey. Let me give you a simple analogy. Imagine you're trying to sort a box of mixed fruit, apples, oranges, and bananas, all jumbled together. A neural network is like having a series of specialized sorting machines. Each machine sorts, tilts, and reorganizes these fruits until, by the last machine, the apples are in one corner, oranges are in the other, and bananas are in the third. The mathematics that describes this sorting, that's linear algebra. Before we dive into these transformations, we need to understand how neural networks even see data. Let's see what the fundamental blocks of building blocks are, which are vectors. Everything that enters a neural network must first become a vector, a list of numbers living in a high-dimensional space. Let me give you some concrete examples. As you can see in the image here, there's an A and there's a grayscale image of Abraham Lincoln. And on the A, we can see that there's a brightness value between 0 to 255. And the first pixel is bright white, and the third and fourth pixel are pure black. So here we can see the vector space multiplication, the vector space representation of the letter A with a bunch of zeros and ones. So what happens is it's flattened into a 148 by 1 matrix, which is 000 till 1. And that's also the case for the grayscale image of Abraham Lincoln. When we feed this into a neural network, we flatten it into a single vector, where each number corresponds to 1 pixel's brightness. And it isn't just about images. Word embedding and works the same way. Let's take the word king instead, right here. Instead of sorting it as a text, we might represent it as something like 0.5 minus 0.4, 0.7, 0.8, and so on till minus 0.6. Let's say, for this case, it's a 7-dimensional vector, but it can be an n-dimensional vector where each dimension captures some aspect of its meaning. Here's where it gets fascinating. In this vector space, we can actually do math with meanings. So king minus man plus woman gives equal to something close to a queen. That's because the vector space geometry captures the semantic relationships. Here's the beautiful part. Each input can be viewed as a single point in the vector space, as we can see in the image to the left, where wolf, dog, cat are in some point in the in an n-dimensional space. So is apple, and so is banana. And this is where the transformation magic begins. The network's job is to take these points and move them through a carefully designed system until they land in the right place.
Powerhouse of neural networks, which are matrix transformations. So in each layer in a neural network applies a linear transformation to an input vector using the formula z equals to w times x plus b, where z is your output vector, which is m-dimensional, w is your m by n weight matrix, your input vector is n-dimensional, and you have an m-dimensional bias vector. So the weight matrix is essentially transforming your n-dimensional input into an m-dimensional output, where each entry in W is a parameter that determines how strongly each input dimension influences each output dimension. So For example, let's say we have the input vector 2, 1, 3, and the weight matrix W, where the first row of W is 0.5, -1, 0.3, and the second row is 0.2, 0.8, and -0.5. And the bias vector B, where B is 0.1, -0.2. Our output vector is given by Wx plus B, so if we multiply W and X and add each dimension of B to it, for the first dimension, we'll get 2 times 0.5 plus 1 times -1 plus 3 times 0.3 plus 0.1 from the bias vector, which gives you 1. And then for the second dimension, you'll get 2 times 0.2 plus 1 times 0.8 plus 3 times -0.5 plus -0.2 from the bias vector, which will give you an output vector Z that equals to 1, -0.5. So you can see that when we're multiplying W by our input vector X, the entries of W give how much each entry of X influences that dimension of Z. So, yeah. So your data lives in space, and a weight matrix essentially reshapes that space. So take, for example, let's say we have a triangle given by the points A, B, C, where A is 1, 0, B is 0, 1, and C is 1, 1. And we apply the matrix transformation 2, 0, 0, 0.5. If we multiply W by each point, A transforms from 1, 0 to 0, 2, B transforms from 0, 1 to 0, 0.5, and C transforms from 1, 1 to 2, 0.5. If we plot each of these points, we can see that our original triangle got stretched out and squashed flatter, which is essentially what happens within each layer of a neural network. So each input vector, which is one sample of your data, in this case, each sample is each point in the triangle. Each of these inputs is transformed by the layer's weight matrix. And so the weight matrix reshapes the space that your data lives in, moving the points around so that patterns within the data can become easier to separate in later layers. However, if we only used linear transformations, we'd have a problem. So let's say we have three weight matrices, W1, W2, and W3, where each weight matrix is applied in each layer. So let's say we apply W1 first, and then apply W2 to the output of that, and then apply W3 to the output of that. We're essentially we're multiplying X by each of these three matrices. However, this is also equivalent to if we multiplied the three matrices together and multiplied that by X. So mathematically, W3 times W2 times W1 can be computed as a single equivalent matrix. So no matter how many linear transformations we chain together, it's still equivalent to performing one linear transformation, which means that using just linear transformations cannot bend or twist our data, but we can't learn complex patterns from that, which is why we need something called an activation function, which introduces nonlinearity. So an activation function is just a function where you put in your output vector from the matrix transformation to get a new output. In this case, we called it A. So some common activation functions include rectified linear unit, often simplified to ReLU. This essentially zeroes out negatives. So you're taking the maximum of 0 and X. So if you have a dimension that has a negative value, it'll become 0, whereas positive values will remain as it is. We have the sigmoid function, which is a historically popular function used especially for early networks and for binary classification outputs, because it maps your outputs from a range of 0 to the range of 0 to 1. Tan H is also another function, which is kind of like sigmoid. However, it's centered around 0, so your outputs will be mapped to -1 and 1, or somewhere in the range from -1 to 1. And then you have a linear activation function, which essentially doesn't really do much since we're already applying a linear transformation. The only thing a linear activation function will do could be to scale it proportionately, which doesn't necessarily introduce nonlinearity. So, for example, let's walk through an example using rectified linear unit. So the function for the activation function in this case is just the maximum, taking the maximum of 0 and x. So in order to apply this function to an output vector, we'll take the example from the very first example that gave an output vector of 1, -0.5. So A in this case, which is the output from the activation function, is essentially just applying your activation function to each entry in the vector. So we'll apply it to 1, which gives the maximum between 0 and 1, which is just 1, and then we'll apply it to the second dimension, which is -0.5. The maximum of 0 and -0.5 is just 0. So if we use this activation function from our first example, we'll get an output vector of 1, 0. As you can see from the original output vector from wx plus b, all this is doing is getting rid of the negative values.
Now imagine stacking multiple layers. Let me walk you through a complete example with a tiny network. Suppose we have an input vector that's 2 dimensions and we want to classify it. For context, each number here could represent a feature relating to the dataset that we've pulled the vector from. We'll be using a 3-layer network to classify it. In layer 1, we're transforming from 2 dimensions to 3. This allows the model to represent the data differently, untangling patterns that were once inseparable in the original space. After we've applied the activation function, we've gained some new information about the vector, and we're going to carry it over to the second layer. In this layer, we're transforming back from 3 dimensions to 2. This allows us to make some meaningful decisions in the future, like class scores. In layer 3, that's exactly what we do. We're transforming to 2 class scores in this output layer, so let's say cats versus dogs. It represents some truth of where the network views the data should belong regarding each of these 2 classes. As you can see, the cat score is much higher than the dog score. What's really interesting is what's happening to our data geometrically at each step. On the left-hand side is an example of this, where we might start with something that's really intertwined, maybe a spiral pattern. Obviously, the data points aren't linearly separable. But on the right-hand side, we can see the eventual output of our neural network, which is grouping together similar data. Our big question is, how has this been done? In this visualization, you can see how a neural network might change the space in order to reach its results. The different layers will rotate and stretch the space, causing the spirals to separate through nonlinear transformations. We end up with something that is linearly separable, as shown by the straight lines for the groupings of data. Here's a real-world analogy. Imagine you have a tangled ball of red and blue yarn. That's your input space, and it's hopelessly mixed. The first layer might loosen the knot a little bit. The second layer separates some strands. The third layer pulls them completely apart. By the final layer, you have all the red yarn on one side, all the blue yarn on the other. The network learned the sequence of pulls, rotations, and untanglings needed to separate them. This is exactly what we mean by progressive linearization. Complex patterns in the input space become linearly separable in the final output space, as shown by the input on the left-hand side to the output on the right-hand side.
So how does the network figure out what these matrices should be? This is where learning comes in, and it's all about gradient descent and backpropagation. The weight update rule is as follows. The updated weight is equal to the initial weight minus eta, which is the learning rate, multiplied by the partial derivative of loss with respect to W. That partial derivative is the gradient of the loss with respect to the weight matrix W. Let me show you how this works with a concrete example. Suppose we have a weight of 0.5 and we compute that our gradient is 0.3. Our learning rate eta is 0.1. The update would be 0.5 minus 0.1 times 0.3, which would give us 0.47. Now let's trace through a real example of how a weight might get updated. Let's imagine we have a network that classifies between images of cats and dogs, and we pass to this machine learning model an image of a cat, like the one that we have on the left. We note that the ground truth encoding for this image should be 1 for the cat and 0 for the dog. However, since the model isn't perfect, its predicted encoding varies slightly from the truth, and therefore we end up with a small error as shown in the last row. But even small errors matter, and we calculate how each weight contributed to this error, and we'd adjust it accordingly. Here's what's actually happening with the mathematics. Let's say we have a weight matrix W in our network, and it's a 3x4 matrix with 12 elements in it. That weight matrix might look like something that we have on the top left of the screen right here. Through backpropagation, we don't just adjust one gradient, we calculate a gradient matrix of the same size, 3x4, where each position tells us how to adjust the corresponding weight. And the gradient matrix would look like something on the top right. And with the learning rate, for this example, let's assume that the learning rate is 0.1. We update the entire matrices at once with the formula given right here in the middle, which is very similar to the one that we saw in the first example. This is matrix subtraction, where each element gets updated simultaneously. For example, if we look at the element in the updated weight matrix in the first row and the first column, we see that we took the value from the original weight matrix, 0.7, and subtracted the first value in the first row and first column of the gradient matrix, 0.02, and multiplied it by the learning rate, which was 0.1, to get the updated weight matrix of 0.698. Now, let's trace what happens to this entire matrix during training. We're building a network to classify cats versus dogs, and we're watching how one weight matrix evolves. Initially, our matrix might look random, numbers scattered between 0 and 1, and the network makes terrible prediction, giving us a very high loss. We compute the gradient matrix and update all the weights simultaneously using matrix operations, and repeat this hundreds and sometimes even thousands of times on images of cats and dogs. The matrix then sets into its optimal configuration with a low loss. Each of these 12 numbers has found its sweet spot through this process of matrix-wide updates. And the matrix now encodes a meaningful transformation, and it's learned to extract features that help distinguish cats from dogs. And this is why linear algebra is fundamental to neural networks. Every forward pass multiplies matrices, every backward pass computes gradient matrices, and every update subtracts matrices. Imagine you have matrices of knobs arranged in grids, and you're adjusting entire grids simultaneously. That's gradient descent operating on matrix structures, billions of parameters organized in matrices, all being fine-tuned through linear algebra operations.
Okay, let's move on to a real-world example, which is recognizing handwritten digits. On the left, we have lots of numbers written by hand. Let's take the 6 on the right for example. It's made up of 28 by 28 pixels and can be grayscaled as seen with values between 0 and 255 for each particular pixel. Let's flatten this into a 784 dimensional vector. This would look something like 0, 0, 045, 200, 255, 210, etc., as depicted. We will use this vector for layer transformation and in order to do so, you must use the aforementioned equation for weighted matrices. We will be using a 784 by 128 weighted matrix to multiply for the first layer. This gives us 100,352 individual weights. We can represent this as a colored heat map like the one to the right to help visualize. Each of the 128 output neurons are computing a weighted sum of all 784 pixels. For example, neuron 37 in layer 1 might learn to detect vertical lines. Its weights might be high for pixels in a vertical column and low everywhere else. When it sees your 6, which has a vertical stroke, it activates strongly. Maybe outputs 4.7 after the transformation. Then our 128-dimensional vector might look like 0, 2.7, 0, 0, 4.7, etc. We will repeat this process for our second layer transformation with the 128 by 64 weight matrix, and then once again for our final layer transformation with the 64 by 10 weight matrix. This will produce our final 10-digit vector along with our final scores. There are 10 scores, one for each digit 1 through 9. As you can see, the 6 class has by far the highest value, meaning that we have correctly identified the handwritten digit as a 6. However, in the event that we had gotten it wrong, for example if we wrote a messy 6 that looked like an 8, and the network predicted 8, we could compute the error and propagate it back through all the layers. This would adjust the 100,000 plus layer weights slightly, so that the next time we write a sloppy 8, it'll be much more likely for the network to get it right. Right. So to bring it all together, neural networks are machines used for identifying data and making predictions about composing and refining matrix transformations. And now you've seen exactly how that works with real numbers and examples. Okay, so inputs are vectors representing any point in high-dimensional space. Weights are matrices that transform these vectors, reshaping the geometry of our data space at each layer. Layers are compositions of these transformations. A simple input like 3, 2 can become 2.11, then 1.48, 0.51, then 1.24, 0.015, progressively disentangling complex patterns until they become simple and separable. Activations introduce nonlinearity, and rectified linear units can turn negative 0.5 into 0, creating those crucial folds in space that prevent the network from collapsing into a single transformation. Remember, neural networks are math, not magic. They're vectors being multiplied by matrices, transformed through layers, and optimized through gradient descent. From recognizing your face to translating languages, it's all vectors, matrices, and transformations. Thank you for watching.